1, 2, 3. It has been a while. Not really too long, like maybe 2 days. I realize like maybe it's best I only stream for 6 days a week, not 7 days, because I think I need time for my sleep to catch up. So I took one day off and then I was like, hmm, I should maybe take my day off on Sundays, well, Saturday nights. So Sunday church would be a little bit better. So that's what I'm gonna do now. 6 days a week, but not Saturday. Um, anyways, it's not like I didn't read the book. I cleared up some confusion. Like the biggest thing, I did a bunch of stuff. Like I computed a bunch of these stuff, but um, like one of the biggest conclusions I drew was realizations was where is where is the U? It's somewhere. The orthogonality rules or something. Um, ah, okay, here. So the definition of matrix multiplication is Cij equal the summation of Aik Bkj. I was confused as how they got from here to here, but as you see, I wrote definition of matrix multiplication. To get from here to here, um, this is basically Cij here, and this is AKI Bkj. Yeah, so yeah, and the same can be done here. So I was confused earlier how they got from here to here. It's just a definition of matrix multiplication. We move. Um, okay. Okay. I think I'll start from here. Woof. Simultaneous equations. Determinants are also involved in the solution of simultaneous equations. We have n algebraic equations and unknowns. These equations can be written down very compactly, matrix form. A is m by n matrix and x is and c is n d column vectors. Left multiplication gives us this if A inverse exists. This requires a determinant of A is not equal to 0. That is, that A be non-singular. Okay, let me write this down. A inverse equal cofactor matrix transposed over the determinant of A. If determinant of A is not equal to 0, that means the inverse exists, which means it is invertible or non-singular. Okay. This requires a determinant of A is not equal to 0, that is, that A be non-singular, and it gives xi equal this, yeah. The numerator of this expression looks like a Laplace development of the ith column of a determinant. Laplace development of the ith column of a determinant. So the Laplace is just this multiplied by this determinant, this determinant. Yeah, this is cofactor is basically the determinant factor, and this is just the element, right? CJI. Yeah, I can see it. This is indeed the case. The determinant is that of A modified by replacing the ith column by C. Cramer's rule. I haven't really looked too much at Cramer's rule or the Pauli spin matrices. Okay, homogeneous equations. It's also possible to solve a set of n homogeneous algebraic equations written in the form Ax equals 0 with C equals 0. It's obvious that there is a unique solution where the x is equal to 0. If A is invertible, we call this a trivial case. A non-trivial solution, it's obvious that there is a unique solution x if A is non-singular. If A is invertible. Okay. If A is invertible, we can put A minus 1 here, right? Is anything multiplied by the 0 vector a 0 vector? This times this because it gives you 0. This, yeah. Yeah, anything times a 0 will give you 0, which means x will be equal to 0. We'll call this a trivial case. A non-trivial solution is one with x not equal to 0, so x actually has stuff in it. This can only occur if determinant of A equals 0. Okay, if A is not invertible. But then we can have quotient of 2 zeros, which can be finite. Quotient of 2 zeros. I guess we're talking about here, right? C is a 0, and A inverse would be a 0. Cofactor matrix transposed. This would also be 0 and 0, right? Would it? Okay. Let's first consider the simple case of 2 by 2 matrices. Ax equals 0 means two simultaneous equations. Yeah. These equations state that x is perpendicular to the row vectors. State that x is perpendicular to the row vectors a11, a12. Yeah, contained in A. That is, x is a vector, any vector, perpendicular simultaneously to both a1 and a2. Its length is of no consequence, only the direction can be determined. If the two row vectors are non-parallel, if the two row vectors are non-parallel, so like this would be non-parallel, determinant of A does not vanish. There is then no non-trivial solution. Parallel. Okay. So if they're parallel, right, that means their components are kind of like the same, maybe with a negative involved for anti-parallelness. So if they're parallel, their numbers are basically the same, which means the determinant is 0 because two identical rows or columns means the determinant will be 0, right? So if they're non-parallel, that means non-parallel means the rows not identical, which means the determinant is not 0. So I wonder if any, like for when we get deeper, if any two are parallel, does that mean determinant is 0? And does that make it Um, hmm, it's obvious that there's a unique solution. Trivial case. Determine A equals 0. That means there's non-trivial solution. Okay. Um, um, if two are non-parallel, determine A does not vanish, so there is a determinant. Um, there is then no non-trivial solution. The reason is that A1 and A2 already span the entire 2D plane of the problem, and X perpendicular to this plane cannot also lie in it. Okay, so what they're saying is X can't be here because X needs to be perpendicular to both. X is not perpendicular to both here. If X is perpendicular to this one, it's no longer perpendicular to this one here. If X is perpendicular to this one, he's not perpendicular to this one. And since it's a 2 by 2 matrix, we're only in 2 dimensions, so they're hogging everywhere. X cannot, there's no solution for X. Cannot, an X perpendicular to this plane cannot also lie in it. There's thus no solution X in the plane. This is the reason why determinant A equals 0 is required. Determinant A equals 0. Yeah, if determinant A equals 0, that means they're parallel, which means X can occupy this. X can be here and here and here, perpendicular to the guys, right? Determinant A equals 0 can be obtained by making A1 and A2 parallel. Yeah, correct. They then occupy only one of the 2 dimensions of the problem, leaving the other dimension for X. Yeah. The direction of X is then uniquely determined up to a sign. Okay. But your matrix AX equals 0 means that X must be perpendicular to true stuff now. Suppose two of these guys non-parallel. To obtain determinant A equals 0, the Taylor vector must be made up of a combination of these non-parallel. The Taylor vector, to obtain determinant A equals 0, we want them to be parallel, right? The Taylor vector must be made up of a linear combination of these non-parallel vectors. So if this is true, if A3 can be represented as like an amount of A1, like a multiple of A1 and A2, then this is parallel to, oh, that just means that lies in this plane, which means X has the 3rd dimension all to himself to be perpendicular on. No one is touching him. He's perpendicular to everybody. Let me write this down. Must be in the A1, A2 plane. Okay. Equation this states that A3 lies in the plane. Thus the 3 row vectors span only a 2D. Now shows that X is a normal to this plane. This now shows that X is a normal to this plane through the origin. All vectors are measured from the origin. Why? Over again, only its direction is determined, not its sense or length. Hmm. Okay. Boom, boom, boom. A1 and A2 make up this plane. Make up this plane. Um, X must be perpendicular to all of them, right? So X can go here. No, you can go backwards. Only its direction is determined, not its sense or length. Just say its direction is determined, but is this not two directions, or are they counting this as one? I'm gonna assume they count it as one, because that's what they're saying. Only it's, unless they would say like it's two directions, right? Determine A equals 0 is also realized when all three row vectors are parallel to one another. So if all three parallel, that means X can be perpendicular like this, or it can be perpendicular to like this. So X X has a whole plane to himself, basically. Um, so 0 is when all three row vectors are parallel to one another. These vectors span only 1D subspace, specified by the common direction. These vectors, EA1. Any vector in the plane normal to EA1 that contains the origin is an acceptable solution. That is, the solution X spans this 2D plane perpendicular to EA1. Hmm. Wait, so if they're saying all the vectors must be at the origin, right? That just means, so all vectors must go through the origin. That means that the parallel guys we're talking about are literally on top of each other, because they must go through the origin, and they must have the same, like, direction. So they're literally just one line. Um, in both cases, the solutions span the subspace. The solutions span the subspace not spanned by the row vectors of A. These considerations, this could be generalized for n by n. The row vectors span R dimensions, R-dimensional subspace SA, with R being less than n. The row vectors span R dimensions, R-dimensional subspace SA, with R being less than n if the determinant is 0. The solutions X of the homogeneous matrix the solutions X of the homogeneous matrix equation A equals 0 span the n minus R dimensional Sx. Okay, SA and Sx. SA is the subspace A, the row vectors of A, like span. Sx is the subspace X spans. The subspace Sx is called the orthogonal complement of this subspace SA. These subspaces are orthogonal to each other. They make up an ND space together. It makes sense. If R equal n minus 1, n minus R equal 1. If R equal n minus 1, n minus r equal 1. Yeah. Well, what is the point of this? Then ax equals 0 determines one direction only. Okay, we're dealing with n dimensions, right? N is 3D. Let's say n is 3D. If r equal n minus 1, r is 2D now. 3 minus 1, 2. N minus r equal, this is a nothing burger. R, R is subspace SA. Okay, which means SX only has one dimension. AX equals 0 determines one direction only. More generally, AX equals 0 determines the n minus r linearly independent directions. AX equals 0 determines the n minus r linearly independent directions that specify the subspace Sx. Okay. Okay, the homogeneous equation has solutions which satisfies that will satisfy the equation. Yeah, because this times this equal this. They are vectors lying in the plane. They are vectors lying in the plane perpendicular. Yeah. So these three are parallel. All three are parallel, which means there's only one unique thing really going on here. So r is 1. So n minus r is 3 minus 1 equal 2. SA has one dimension, and SX is 2 dimension. Has solution satisfy this? They are vectors lying in the plane perpendicular to the row vectors. Yeah. Solve this. Okay. First we have to check if the determinant. First we have to check what's going on with the determinant. Okay. Determinant is 0. What does that mean? Determinant being 0. Oh. Determinant being 0 means that two guys are at least two guys are parallel to each other, which means there's at least one solution going on. If determinant was not equal to 0, that means each of these guys, there's no parallelness going on, so they occupy the entire space, which means there's no sense doing the maths. We know this. There's only the trivial solution, right? Trivial and non-trivial. A non-trivial solution is one way x. Okay, yeah. So if all these guys, if determinant is not 0, then we only have the trivial solution, where x vector equals the 0 vector. By Laplace development of the first column. No, this. Okay. A3 equal A1 plus A2. This equal this plus this. So yeah. So that the three vectors are linearly dependent. Finally, we throw out A1 defined. What do you mean throw out A1? this times this, x minus x1 plus x2 plus x3 equals 0. x1 plus x2 plus x3 equals 0. 0 plus 2x2 plus 2x3 equals 0. Why are we... Okay, this is from row 3, matrix multiplication. This is from row 2. Row 1 would be minus x1 plus x2 plus x3 equals 0. Why are we throwing out this one? Um, hmm. I know it doesn't give us any additional information, but x1, x2, we know that a3 is a1 plus a2. Linearly dependent. We throw out a1 to find the two independent equations. Why are we getting rid of a1? Um, hmm. Okay, from here we can see that, from these two we can see that, no, we can't see anything really. I was gonna say x1 is it? Okay, so 2x2 plus x3 equals 0. If we divide both sides by 2, we get x2 plus x3 equals 0, which means x1 is literally nothing, question mark? Maybe? Are we allowed to do this? Divide them by 2. Does that get rid of information somehow? x2 plus x3, let's just continue. The solutions are x1 equals 0, x2 plus x3 equals 0. X1 equals 0, x2 plus x3 equals 0. Along the line x, ah, I'm opening stuff by accident. The solution can be obtained even more readily by using the result that x equals xi, x2, x3 is perpendicular to both a1 and a2, hence x equal x is perpendicular to both a1 and a2. X is a cross product of a1 and a2. a1, a2. I suppose constant 0 to minus what does this mean? Constant x2. Okay, I am a little confused. Homogeneous equation, this. We get these three equations. We saw that determinant a equals 0, so we know there is at least one solution in there. We note that this. But what if it was so complicated that we couldn't figure it out? Like this relationship here. Let me just draw them, I guess. So minus 1, 1, 1. 1, 1, 1, 0, 2, 2. Okay, I have done nothing. 0, 2, 2, 1, 1, 1. Where's 1, 1, 1? They all lie in the same plane, right? Okay, okay. What if I got rid, like, what if I didn't care about this equation instead? I would be left with minus x1 plus x2 plus x3 equals 0. And 2x2 plus x3 equals 0. If we're allowed to do this, we divide both sides by 2 to get x2 plus x3 equals 0. Substitute this into here to be like minus x1 plus 0 equals 0, which means minus x1 equals 0, which means x1 equals 0. What if we got rid of this one? If we got rid of this one, then um, do we need to resort to simultaneous equations? Well, but by that I mean, do we need to add them together? We're doing simultaneous equations anyways. Like, this counts as simultaneous equations, so what I said there doesn't make sense. Okay. X2 plus x3 equal x1. X2 plus x3 equal x1. I'm getting that from here. We can sub this in to here to get 2x1 equals 0. x1 equals 0. We're never really given information about x2 or x3. What if we try to force it? x2 equal x2 equal minus x3. That's correct, right? You can get that from here. You can get the equation x2 equal minus x3 plus x1. You can get the equation x2 equal minus x3 minus x1. And for this to make sense, x2 equal this bling minus x3 plus x1. Plus x1 minus x1, bring this across, 0. I don't know what I'm doing to make these, there's some weird stuff happening. Okay, let's just continue. I think, okay. I was gonna continue, but then I realized I didn't touch on this at all. The solutions are this. Yeah, I agree. Along the x equal x2, 0, 1, minus 1 in the 2, 3 plane. Along the line x equal x2, 0, 1, minus 1. Where do we get this? The solutions are this. Along 0, 1, minus 1. x2, okay, x2. Why we focus on x2? Okay. I I think I get it. Maybe. Okay, so we confirm that x1 is equal to 0, right? So in our x row vector, x1 is 0. We saw x2 equal negative x3. So if this is x2, then this could be negative x2. You factor out x2 because it should be a scalar, right? Does it make sense if this is a vector ever? Row vector 0. Does that make sense if that is ever a vector? Bling, bling, bling. Anyways, you can just factor out the x2 to get this. Another solution is x equal x3, 0, minus 1, 1. Well, what plane would that be in? Would that be in like, is there something such as in negative 2-3 plane? What is the 2-3 plane? The 2-3 plane. 1, 2, 3? x2. I think they're saying x2 could be negative as well, which means it can go in the opposite direction. Ah. Anyway, let's just continue. Linearly and linear independence of vectors and the rank of a matrix. The solution of the problem: linear independence of vectors and the rank of a matrix. The solution of the problem of homogeneous matrix equation given so far is adequate, but sketchy for the general case. The inquisitive reader who must know how things work out in detail should read on. Suppose only the first R row vectors AI. Only the first R row vectors AI of A are linearly independent. The remaining n minus R vectors AK are linearly dependent on the former in the sense that they can be expressed as linear combinations. AK equal going from 1 to R, C1, yeah, this makes sense. Okay. A AI AK independent dependent. This means that if a vector x is orthogonal to all the independent guys, ai dot x equals 0 for I equal 1 to r. Oh, I should write that um uh there's r guys here and there's n minus r guys here. Yeah, this means that if a vector x is orthogonal to the AIs, it is automatically orthogonal to the AKs as well, yeah. Um, this can be written more compactly in matrix form. Bx equals 0, where B is an R by N non-square submatrix of A containing the linearly dependent. B is the R by N submatrix containing the independent guys, and X is the normal n by 1 column matrix. Can be written more compactly. AI dot X. Okay, so okay, um, so we're just talking about this. We can literally draw the submatrix and the matrix because they said the first are row vectors, so they're not really spread out, at least in the introduction. So we have 1, 2, 3. We have R rows and the normal n columns because we're always dealing with square matrices because to get a determinant, it needs to be square anyways. So n by n. So this is r times n. R times n. ai dot x equals 0. So this is, yeah, ai dot x equals 0. More compact in the matrix form bx equals 0. Yeah. ai dot x equals 0. ai dot x. Okay, yeah. Okay. What b is, yeah, r independent, x is n by 1, yeah. Okay. The R times n non-square matrix B contains n column vectors bj. Blung, 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 blung. Not all of these are linearly independent of one another because an arbitrary RD vector has at most R independent components, yeah. No more than R of these column vectors are linearly independent. So B has n column vectors. Not all of these are linearly independent of one another because an arbitrary RD vector RD has at most R independent components. Consequently, no more than R of these column vectors. Okay. B. What color do I use? Yellow, I guess. Column, 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 column. We have n BJs. n bj columns. Yeah. Um, if and all these guys have R components, right? So let's say R is 3. So B1 has 3 components. Bling, bling, bling. Um, uh, if we want B2 to be non-parallel, i- B2 could be non-parallel, B3 could be non-parallel, but B4 cannot be non-parallel because, um, okay, for a 2D space, right? 2D, 2D, this and this, non-parallel. Hmm. Hmm. Okay. Okay. For a 2D space, it's impossible to get 3 completely independent guys because the third guy can be expressed as like a combination of the first 2 guys. Because that's how planes work? Question mark. I believe so. That's how I believe they work. And the same thing with 3D now. Um, with 3D, there's only 3. Like you can only make 3 non-parallel guys. The fourth one will be a combination of the 3 non-parallel guys. So yeah. So we have R independent guys, and once again n minus R independent guys. All right. Um, a column vector say Bn linearly dependent on the other column vectors. Okay, Bn contain n column vectors. Bj. Not all these are. So Bn is the name for dependent guys. Bn equal dependent. Dependent. DJ Bj. We're calling Bj as the independence. Bj equal independent. And we're saying Bn is equal to summation from j equal 1 to j equals to 1 to n minus 1 is related to this n here. Bn equal j equal 1 to n minus 1. But what if this particular Bn is the second Bn here? Does that mean we're summing up the first 4 guys? Even though only the first 3 guys will do the job? J equal 1 to n minus 1. Should it not be j equal 1 to... What would it be then? J equal 1 to j equal r? Yeah, I guess. Maybe that's the thing, right? Maybe n minus 1 equal r. Does that make sense? You have the whole space minus the subspace equal, no, I don't think so. So let's just continue. A column vector says, it's not like this hurts, right? Does it? Hmm. DJ, BJ. You have a constant. DJ, BJ. J equal 1 to n minus 1. Bn equal a number times b1. Okay. So not only does this change, wait, v1, v1, d1, d1, v1, d2, v2, d3, v3. The column vector dependent on the other column vectors is written as this. Can be dropped from the matrix B without affecting the linear independence of the remaining n minus 1d. So we're saying we can remove the dependent guy without affecting the linear independence of the remaining row vectors n minus 1. Wait, why are we going n minus 1? Should it not be n minus r? N times 1 column matrix. Okay, B is r times n. B is r times n, rows times column. X is n times 1 column matrix. N times 1. So the result should be, we have r times n, and then n times 1. So the result should be r times 1. R times 1. 1 r. The r times n non-square matrix contains n column vectors bj. Not all these are independent because an arbitrary RD vector is at most r independent. No more than r of these column vectors are linearly dependent. So B is made out of these guys. If we're dealing with 4 guys, if R is 4, then only the first 4 column vectors, only the first 4 column vectors are truly the independent. No more than r of these. A column vector, say Bn linearly dependent on the other guys, could be removed from the matrix B without affecting the linear independence of the remaining n minus 1d rows. Now we're talking like specifically. So this guy specifically could be removed and he wouldn't affect. So let's say this is B5, right? B5. Without affecting the remaining n minus 1. So B5 could be entirely removed and wouldn't affect um, the remaining 40 row vectors. This is because B5 does not contain any information not already contained in the remaining vectors Bj. You can scrap this entire section. Can we really though? Bling, 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 bling. Bling, 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 bling. There are exactly n minus r of these linearly dependent column vectors. N minus r. Yeah. That can be discarded for the time being. We now have an r by r submatrix R phi. Yeah. Made up of the remaining guys. If we try to discard any more, we'll end up with a non-square matrix in which row vectors have fewer than r components each. Yeah. Should this happen, not all the r row vectors. Not all the r row vectors in the matrix can be linearly independent. We'll end up with in which row vectors have fewer than r components each. Not all the row vectors. Can be linearly independent. Should it not be all the column vectors? Anyways, we move. The point is, you'll lose some stuff. Not all the r vectors still in the matrix can be linearly independent. By construction, we have obtained r by r square matrix R containing r linearly independent column vectors. Its determinant does not vanish because there's no parallel guys. Hence, R is a non-singular. You could find the inverse. The order R of the submatrix R is called the rank of the matrix A or B. The order of the submatrix is called the rank of the matrix A or B. So A is the original guy. B is, how do we even get B? B is from all the independent row vectors. Row vectors from A. The order R of the submatrix R is called the rank of the matrix A or B. So rank isn't actually about how much rows and vectors. Rank is about how much independent rows of vectors. Because otherwise they would have a different name, like the mega rank. Unless this is a total contradiction, like two names for this same name for two different things. I'll drink some water. I must say I am considerably less confused than last stream. Maybe it has something to do with how sleepy I am. I don't know. I'll bump down the confusion meter. No, that's sleepy meter. I'll bump down the confusion meter to green. Okay, some problems. The matrix eigenvalue problem is an experimental fact that the linear momentum of a massive object, an object with mass p equal mv, is always parallel to its linear velocity v. In contrast, the angular momentum L of a rigid body is not always parallel to its angular velocity omega. Parallel to angular velocity. A classic illustration of this observation is a rotating dumbbell over here. Is made up of 2 point masses connected by a massless rod 2r, rotated about midpoint O, about the z-axis. Okay, with angular speed omega. The angular momentum L equal r cross p is always perpendicular to the dumbbell axis. So we're calling dumbbell axis. L is always perpendicular to the dumbbell axis. I guess that's the rotation axis. Consequently, it is not always parallel to omega. However, both L and omega are 3D column vectors when expressed in matrix notation. 3D column vectors. Hence, there exists a 3x3 square matrix in special I that can connect them. Special I is called the inertial matrix. Linear momentum, P equal mv, always parallel. So you push an object in this direction, boom. The momentum is calculated along this direction. Angular stuff has always been like a confusion point for me, like for momentum specifically. Because like the direction of this doesn't really make much sense to me. The angular momentum L of a rigid body is not always parallel to its angular velocity. P a classic illustration of this observation is a rotating dumbbell. It made of 2 point masses M connected by a massless rigid rod length 2r, rotated about its midpoint 0 about the angular speed omega. Angular momentum L equal r cross p. So r is here. P, if you're being rotated like this, in the moment, P should be like this, right? Right? R cross P would be up, right? Like, why is R cross P here? Unless this is just weird, like the diagram is weird. So it's being rotated like this. Being rotated like this. R is the position vector, right? R is the position vector of the mass. P is the linear momentum of the mass, which I assume is tangent. V V velocity. And let me continue reading. The angular momentum L equal R cross P is always perpendicular to the dumbbell axis. R cross P. It is not always perpendicular. It is not always parallel to omega. However, both L and omega are 3D column vectors. 3D column vectors. When expressed in matrix notation. Hence, there exists a 3 by 3. Hence, truth when expressed in. So if two column vectors exist, there must be a matrix connecting them. Like that's just a fact about matrices. Let me Google that. I've had the idea of like having like an overlay where like usually it's be right back, like come back soon. But instead it's like I am Googling stuff right now. Is this how the matrices work? Question mark. Let's say I have two matrices A and B. Is there always a matrix that can convert A into B from multiplication? Whether a matrix M exists to convert A into B depends on the dimensions of A and B. Whether A is invertible, whether A of B is related by linear transformation. If A is square and invertible, then yes, M equal B A to the minus 1. If A is not invertible or not square, then a solution might exist, but not always. You might need to use least squares methods. Okay. So I should look into like inverses. So the question is, if I have a matrix A and I have a matrix B, is there always a way to turn A to B from matrix multiplication? So A equal MB, or A B equal MA. Well, it's the same thing, right? Just switch them around. AM equal B. M would be A inverse B. And this can only happen like if they're this can only happen if A is invertible and if AB can be like multiplied, like the dimensions allow it. And I'm just like parroting what Google told me. And it makes sense so far, right? So 3 by 1. 3 by 1 Wait, no. Tree by tree. It's not always parallel. A tree by one can't get like inverted, so it has to be a tree by tree, right? Which means this needs to be a tree by something. Tree rows. Tree rows endless amount of columns. Hmm. Okay, let's just continue. Alan omega tree the column vectors when expressed in matrix notation. Hence there is a tree by tree matrix I. Connect them. I is called the inertial matrix. So L equal special I omega, or the I component of L equals I component of L um the sum of, so we're summing because we're trying to get a component of the matrix multiplication, and matrix multiplication is um to get an element from a matrix multiplication, there's always like a sum involved. So like Li I. So if we're looking for L2, right? L2 equal the sum of all the J L2, all the J guys, I2, I2J, omega J, 2J, row, second row J. So all the elements on the second row of I multiplied by J, because this is a 3 by 1, so you can't really go left and right. But if this wasn't a 3 by 1, I assume it would be like Ji or something, because that's all the definition of matrix multiplication is. Question mark. I is called the inertial matrix for the special case of a point mass. We have, with the help of the BAC rule, L equal M. So this is separate, right? L equal MR cross V. For the special case, we have the help with the BAC rule, L equal MR cross V. I believe this is just a physics equation. MR cross omega cross R V plus here MR cross omega cross R M uh I trust this, but let's just go back to the BSC rule. BSC rule is should be here. BSC, where are you, my friend? My good friend. Over here. A cross B cross C equal B dot C cross A. No, it's over here. A cross B cross C equal B A dot C minus C A dot B. Yeah, B dot C cross B dot A cross B A dot C minus C A dot B. Yeah. 90 something. Okay, yeah. So M R cross omega cross R. R cross omega cross R equal uh omega is B, right? So omega A dot C is R dot R minus R R dot omega, which is R squared omega R squared minus R dot W. And we're allowed to put the R squared in front here because this is a constant, right? This is just a magnitude times a magnitude. And all this has a M happening in front of it. So M R squared omega minus M this stuff M L equal special I omega. L equals special I omega. I equal L over omega, which you get from here. You get here from doing like inverse stuff. So right multiplication of omega to right multiplication of omega inverse. You get I on this side, you get L omega minus 1 here. L divided by omega, this thing divided by omega, this disappears, this omega disappears, and what do we do about this? Apparently you just leave a blank space, apparently. That's weird. If I were dividing this by omega, what would I do? R dot W. What is omega? Omega is a vector. I'll come back to this later. Let's just accept that this is the case. Although R dot blank is weird in vector notation. To write a relation in matrix notation, we note that Li equal M. Oh my god. To write a relation in matrix notation, we know that Li equal M. Okay, well, we're taking it from here. Are we? Yeah. M R squared omega I minus xi summation j xj xj wj r dot omega. R dot omega. R dot omega means ri omega I plus rj omega j plus rk omega k. Why are we summing J? Minus xi. Hmm. Hmm. Equal summation on mr squared. Oh my god. Why are you here? We're factoring out omega j for some reason. Omega j from here. And from here. Are we allowed to do that? Omega j, omega j, omega j. Let's just go with it for now. I will come back to this. I know how it worked for here, right? Because in order for this, oh my god, it's weird. Chronicle deltas is weird. Okay. Fine, I know how it works. Comparison with equation 2.47. What is that? That's up here. Gives iij equal mr squared bling minus xij in matrix notation. Having established that L is in general not parallel to omega, we may ask next if occasionally they might be. It's easy to see that for a rotating dumbbell there are indeed three distinct directions along which this occurs. One of these omegas is parallel to the dumbbell axis. Theta equals 0. Parallel to the dumbbell. What is the dumbbell axis? Is the dumbbell axis this axis? What is axis? Because I thought it was this axis because they were like the angular momentum is always perpendicular to the dumbbell axis. And this showed this was L, which looked kind of perpendicular to this, but it's also perpendicular to this. Is all the angular momentum is always perpendicular to the dumbbell axis if theta is not equal to 0. So if theta is 0, L is not perpendicular to the dumbbell. If theta is 0, L is not perpendicular to the dumbbell axis. Why? Is it because R, it would line up with R? I think so. I, I think so. R. Consequently, it is not always parallel to omega. Not always parallel to omega. We move. One of these omegas is parallel to the dumbbell axis. I still don't know what the dumbbell axis is. It's always perpendicular to the dumbbell axis. If theta not equal to 0, it's not perpendicular. So if R and L okay, I've suddenly gotten a little more sleepy. I'll update the meter. Boom. More sleepy. Okay, well, let's just roll with it, right? One of these omegas is parallel to the double axis, theta equals 0, while the remaining two are perpendicular to the double axis. So the double axis is fixed. The double axis is the x-axis, like where theta is 0. Is that what it's saying? Okay, 1, 1, 1. Well, the remaining two are perpendicular to the double axis, theta equal pi and 2. These directions are called the principal axes of inertia. The corresponding initial inertial parameters. These directions are called the principal axes of inertia. The corresponding inertial parameters. The proportionality constant lambda equal Ln omega are called the principal moments of inertia. The existence of three principal axes of inertia turns out to be a universal property of rigid bodies, as we shall now show. The parallelism between L and omega along these special directions is expressed by the condition I omega equal lambda omega, where the scalar proportionality. What am I even reading? What am I even reading? Okay. Boom, boom. What is the problem? The angular momentum is not always parallel to the angular velocity. I guess that's the problem. Li, Li, I, Ij. Inertial matrix. If we know the inertial matrix, we can go between these two guys. What is this guy? What is this guy? L is in general not parallel. How did we establish this? L is not parallel in general to omega. That means the determinant exists, right? If the determinant in general exists, then we can be like, yeah, it's in general parallel to omega. If omega is in L, like a rho in L, oh my god. Ah! Hmm. I is called the initial matrix. L equal m r cross v. L equal m r squared omega minus r. You can get the angular momentum from the angular velocity. The angular velocity. R squared minus RR. You can get a component of the angular momentum. Angular, yeah. From Angular velocity. Angular velocity, position vector. You can get the inertial matrix from yeah, this is weird. This is weird. I'll end soon. I'm gonna establish that Ln is in general not parallel to omega. How did we do that? How did we establish this? Just from physics. We may ask next if occasionally they might be. It's easy to see that for the rotating dumbbell, there are indeed three distinct directions along which this occurs. One of these omegas is parallel to the dumbbell axis, while the remaining two are perpendicular to the dumbbell axis, theta equal pi and 2. These directions are called the principal axes of inertia. So they're saying two of the directions is from pi and 2. So 1, 2, negative pi and 2? Well, what? 1, 2, 3? What? But if this counts as 2, why doesn't this count as 2? Should there not be 4 then? And, the corresponding inertial parameters. Corresponding. So for each one, there's a parameter. No, for each axis, there's a corresponding parameter. The proportionality constants lambda equal L and omega. Principal moments. The existence of these principal axes of inertia turns out to be a universal property of rigid bodies. Wait, so one is a problem, one is a solution. So all this is just showing us a problem. I guess the problem is to find a solution to this. The parallelism between this and this. The parallelism between L and omega along these special directions is expressed by bling bling equal bling bling, where the scalar proportionality constant is called the eigenvalue of a special I. Eigen is the German word for special, characteristic, proper. This is called an eigenvalue equation. It's interesting observation that this could be solved. Interesting observation that this can be solved for these special directions, omega, and for the eigenvalue associated with each of these directions. We'll stop here for today. I'll look into this later. Okay, I think I just need to maybe get a good grasp of like angular momentum. That has always been a tricky subject for me. The end. Goodbye. Tata. Sleep. Well, I'm not gonna sleep. Well, I might sleep. I should sleep. Goodbye.